So we're going to begin the notes with B, which is a word problem. And there is a picture representing the question. An air tanker flies over the forest and it's dropping water at a constant rate, until the tank is empty. And so we see the equation written, or the function, f of x equals 400x. And that represents the amount of water being dropped from the plane. The question is, what's the domain and range for this function? So it's a real-world application. Well, the air tanker has water in it, as you can see in the picture. And it cannot drop water for a negative number of seconds. So your domain, which is your x values, has to be a number that is greater than or equal to 0. The tanker can drop water for a maximum of however many seconds it takes before it runs out of water. So let's think about that. It says the tank capacity is 8,000 gallons. Water is being released at 400 gallons per second. So if we were to take our calculator and we were to divide 8,000 gallons divided by 400 gallons per second, we would realize that it takes 20 seconds for all the water to be gone out of the plane, out of the tanker. And so our domain, which is our x value, which, as we said in the problem, is given to us x seconds, is going to be written as, and you can write, let's write it both ways. Let's write interval and let's write regular set notation. And so set notation would look like this: fancy bracket, x, such that x is a number between 0 and 20, including both of those. At 20 seconds, there's no more water left in the tanker. At 0 seconds, there's 8,000 gallons in the tanker. If we were to write that using interval notation, that would be square bracket, 0, comma, 20, square bracket. For the range is the air tanker cannot drop a negative number of gallons, and its maximum capacity is 800 gallons. And so my range is going to be anywhere between 0 and 8,000 gallons. And so again, we could write that using our fancy set notation. So y such that 0 less than or equal to y less than or equal to that 8,000 gallons. Or we could use our interval notation 0 to 8,000 with square brackets on both sides of that 0 and 8,000, because we are including the 0 and the 8,000. All right, we're going to move on to a second example that is a real world example talking about domain and range. And this is a car that starts a journey and it has a full tank of gas. And again, the equation for the car is given by this: y equals 16 minus 0.05x. And it relates the number of gallons of gas y. So gas is y left in the tank to the number of miles the car has traveled. It is important when you are working with real-world applications to define what your variables are in the equation, especially when you're being asked to give domain and range, because as we saw in the air tanker, it directly relates to what's going on in the situation. So in that tanker, there was only a certain amount of water in it. And after a certain amount of time, there isn't any more water in the tanker. And that would indicate that the domain and range would have restrictions on it. It's not just any number you can plug in for X and any number that can come out for Y. In this case, you only have a certain amount of gas in your car. And if you drive your car, you're going to use up the gas, and eventually there's going to be no more gas left in the car. So the question is, what are the X and Y intercepts of the graph, and what do they represent in the situation? So I'm going to just zoom up a little so I can see it a little clearer. You can visually see the X and Y intercepts by looking at the graph. So I'm going to go ahead and highlight them in a different color. So I think I'm going to use purple. And so there is my Y-intercept. And there is my X-intercept. So visually, we can see where they are. The graph intersects the X-axis at the point 320, 0. The graph intersects the Y-axis at the point 0, 20. So if we wanted to know what the X and Y intercepts were, they are actual points on the graph. And we would say that the Y-intercept is 0, 16 or 16, and the X-intercept is 320, 0. What do they represent? Well, what it represents is, for the X-intercept, it means the car can travel 320 miles before it runs out of gas. So the car can travel 320 miles before it runs out of gas. Now, if you're driving, sometimes when you fill up your tank of gas, your car technology will tell you how many miles till empty. So that's what this means, 320 miles. And remember, we started the problem by defining X represents the number of miles. The Y-intercept means the car has 16 gallons of gas when it starts its trip. So the car has 16 gallons of gas when it starts the trip. So that is an application of X and Y intercepts. Those points represent something in this real world problem. So at 0 miles, there are 16 gallons of gas in the tank. There's your Y-intercept. At 320 miles, there are 0 gallons of gas in the tank. And hopefully you didn't get to 0 and then run out of gas. All right, now let's look at X and Y intercepts on just a general function. It says, what are the X and Y intercepts of this graph? And then it says, find these algebraically to discover what the zeros of the function are. So now we have a new word. We have a new word, zeros. The X-intercepts are the zeros of a function. The X-intercepts are the zeros. So that's another name that we're going to give to the X-intercepts. To find X-intercepts algebraically, so when you're not looking at a graph, you're going to set Y equal to 0 and solve. All right, so that's going to be 0 equals absolute value of X minus 3. So now we're going to solve that algebraically. And so that's why in the prerequisite skills, I asked you to practice solving absolute value equations. So we're going to add the 3 over to the other side. So we have 3 equals the absolute value of X, which means that X equals 3 or X equals negative 3. or 3 comma 0, because we let y be 0, negative 3 comma 0. Those are my x-intercepts. Okay, to find the y-intercept, you set x equal to 0. So that would be y equals absolute value of 0 minus 3, which is negative 3. And so my y-intercept is 0 comma negative 3. Let's go back before we move on and talk again about what zeros of a function are. The zeros, and you can see how I'm connecting this here. The zeros of a function are the values that when you input them into the function, the output is 0. So your zeros, input values that make output equal to 0. So that's an important new vocabulary word. All right, let's graph now to verify that I algebraically solved those correctly. So again, the good old t-chart. So maybe I'll do -6, -4, -2, 0, 2, 4, 6. And again, I am randomly picking those values, all right? So if I plug in -6 for x, I get +6 minus 3 is 3. If I plug in -4, I get 1. If I plug in -2, I get -1, 0, -3, 2, -1, 4, 1, 6, 3. So let's get those plotted. Just going to zoom in. 1, 2, 3. Hopefully you can see the symmetrical properties of this graph. This is called the absolute value function. And we're going to study that more when we work on the parent functions, but hopefully you're seeing some symmetry here. So let me go ahead and graph that. And let's look at the x and y intercepts. So y-intercept right here. And you can see that's at the point 0, -3. So that verifies what we did in the previous problem. Let's look at our x-intercepts. 1, 2, 3, and 1, 2, -3. So you can see that this one I'm pretty spot on with 3, 0. But this one, using my graph, I'm actually a little off. So what I want to point out to you is sometimes graphing, you will not be able to grab that x-intercept as precisely as you think, depending on whether you're using your graphing calculator or just a grid like I did. So it's always important to know algebraically how to determine the x and y intercepts. So let's recap. To determine the x-intercept, you set y equal to 0 and solve for x. To determine the y-intercept, you set x equal to 0 and solve for y. Okay, you try. So now I'm going to have you graph this using a t-chart, and then you can, if you can determine the x and y intercepts from the graph, great. And if not, then you will have to go back and solve it algebraically. All right, so let's pick some values. So I'm going to pick -3, -2, -1, 0, 1, 2, 3. Now I want you to be super careful And if you notice, again, a prerequisite skill was evaluating. So when we evaluate g of -3, it's the opposite of -3 squared plus 4. I want you to notice the parentheses that I used. So you do not take the opposite of -3 and then square it. You would not be following the correct order of operations there. So pause for a moment, look at how I've put -3 in the parentheses. So now we're going to evaluate. That's going to be -9 plus 4, which is -5. And then we'll go through and evaluate g of -2, g of -1, g of 0, and so on. So g of -2 would be the opposite of -2 squared plus 4. And that's going to be -4 plus 4 is 0. -1 is going to give us 3. So you can go ahead and pause the video and try some of this on your own, and then restart the video to see how you did. So I'll give you a second to pause. Okay, 0 is going to give us 4. 1 is going to give us 3. 2 is going to give us 0. And 3 is going to give us -5. All right, so we're going to go ahead and plot those. Again, zoom in so I can see it a little clearer. 1, 2, 3. All right, so I have some points. I'm going to go ahead and draw the curve. This curve is called a parabola. Okay, so this is a parabola. It is also one of the, or quadratic. It is also one of the parent functions that we're going to work on, and we're going to learn all of its properties. As you can see from my table, I was able, just using the values that I picked for x, to determine my x and y intercepts. So x-intercepts at -2, 0 and +2, 0. Y-intercept at 0, 4. And so if you hadn't figured those out from the graph, you would have had to go back to your algebraic, which is set x equal to 0 to find the y-intercept, and set y equal to 0 to find the x-intercept. Now you might think, well, there's no y in this equation. G of x is the function name for y. So this is y equals -x squared plus 4. So if I plug in 0 for that, -x squared plus 4, and I solve for x, it's going to be -4 equals -x squared. Divide both sides by -1. 4 equals x squared, and therefore x equals plus or minus 2 when I square root both sides. And that verifies our two x-intercepts that we see on the graph. All right, let's talk about some other key features of functions. Positive and negative intervals of functions. All right. So positive and negative intervals are going to occur when the graph of your function is either above or below the x-axis. So above or below the x-axis. And so if we go back even to this graph, hopefully you can see that a part of that parabola is sitting above the x-axis, and the other parts are sitting below the x-axis, right? So let's talk through how do we describe those areas using interval notation. So the first thing we have to do is we have to graph the function. So it says for what intervals is f of x equals x squared minus 9 positive? For what intervals is the function negative? Graph the function. So again, I'm going to go ahead and graph the function. Now, if you have a graphing calculator, it's nice to type this in and you can actually get a picture on it, and that's something I can show you in class, but I want to make sure everybody has a graphing calculator first. So I'm going to go ahead and just grab some values. So -4, -3, -2, -1, 0, 1, 2, 3, 4. And I'm encouraging you to graph lots of points because the more points you have, the better picture you have of your function. And when you go to graph it in Delta Math and in Math Excel, they are going to require lots of points before they will actually graph the equation for you. All right, so I'm plugging in -4. So that would mean I'm evaluating f of -4, which means that -4 is going inside parentheses squared, subtract 9. 16 minus 9 is 7. And then I would repeat that for -3 squared minus 9, and that's going to give me 0. -2 squared is 4 minus 9, -5. -1 squared is 1 minus 9, -8. 0, -9. 1, -8. Now again, you're going to start to see the symmetry of this function. Symmetry meaning that points are going to be symmetric over this imaginary vertical line that this graph has. In this case, for a quadratic, it's called the line of symmetry, and we'll learn more about that when we learn about our parent functions. So when I plug in 2, -5, 3, 0, and 4, 7. So I want you to go ahead and plot those points on the grid while I'm plotting. Again, hopefully for this curve, you can see the symmetric nature of our U, and it would appear that these points on the quadratic or on the parabola are symmetric over the y-axis there. So this is the y-axis, this is the x-axis. Okay. The graph of this parabola, I'm going to go ahead and shade for you the portions of the graph that are above the x-axis and then the portions of the graph that are below. Now, when I say the graph, when I refer to the graph, I am actually referring to the U-shaped curve. So don't be confused when I say graph. I'm not referring to the coordinate plane. I am referring to what you have plotted on the coordinate plane. All right, so I'm going to shade this part purple, and I would describe that as the area or the section of the graph that sits above the x-axis. The other part, I'm going to shade green, and that's the area of the graph that sits below the x-axis. So when you are asked for what intervals is the function positive, the function is positive when it is above the x-axis. When is the function negative? When it is below the x-axis. Now, algebraically, it looks like this. It is positive when f of x is greater than 0, and it's negative when f of x is less than 0. So how do we describe that using interval notation? Well, Let's go back and review interval notation. So if I'm looking at the x-axis, so track your eyes horizontally, down here to the left is negative infinity, and down here to the right is positive infinity. Down here, negative infinity. Up here, positive infinity. When you are describing the intervals over which the function is positive or negative, you are using x values to describe the intervals. So even though the function is positive, when y is greater than 0, so all those purple y values are greater than 0, we are describing that area using the x values. So we begin with the left part of the coordinate plane, and we track our eyes from left to right, and we describe all of the x's. So for positive, it would be from negative infinity. So from negative infinity, so follow my pen there, right? And then as soon as I hit -3, the graph turns from purple to green. And then it is no longer positive anymore. Notice I have rounded brackets because we're not including negative infinity and we're not including -3. Or, so I'm going to use my union. And then when is the next time that, as we are tracking from left to right, when is the next time we see the purple shade again? Starting at 3 towards infinity. And that describes the intervals where the graph of the function is positive. Those are the intervals where the function is positive. The function is negative in the green area of the graph. So the function is negative in the green area. So again, starting from left to right, we would say that the function is negative starting at -3, and then as I track along my x's, the graph, the green area goes from -3 on the x's over to +3. It's important to note that the function is neither positive nor negative at the x-intercepts. So let me say that again, let that sink in. The function is neither positive nor negative at the x-intercepts. So we will never include those when we are writing our interval notation. All right, you try it. For what interval is h of x equals 2x plus 10 positive? Use a graphing calculator to determine. So I'm going to go to my graphing calculator, and I'm going to type in, I know you can't see what I'm doing, but I'm typing in 2x plus 10 under the y equals. Now, if you don't have a graphing calculator, you will have to draw your own grid. You will have to produce your own t-chart, and you will have to plot some points to get a picture of it. So I went ahead and typed it into the y equals menu. So let me just type that down. Y equals menu. Put your equation, hit graph, and maybe zoom 6 to get a nice picture. So I'm hitting zoom 6. And it looks to me like the graph goes like this. That's what I'm looking at on my calculator. All right. And it says for what intervals is this positive? So again, I'm going to go ahead and I'm going to highlight my positive with purple. And I would say that positive above the x-axis starts here towards infinity. So I guess I need to know what here is, see where my arrow is pointing? And the name of that point is the x-intercept. So I need to know the x-intercept of this graph. Well, I know to find the x-intercept, I plug in 0 for y. So 0 equals 2x plus 10. Negative 10 equals 2x. X equals negative 5. So this is the point negative 5, 0. And so to describe where the function is positive, it would be, remember, everything is read left to right. It would be from negative 5, and notice rounded bracket because we're not including it, to infinity. All right. Moving on to example 4. So now that covers positive and negative intervals. So identifying positive and negative intervals. Now we're going to identify, and I want to stress that when we identified the intervals, those intervals represented x values. All right. Now we're going to identify intervals where the function is increasing or decreasing. In order to do that, we have to know where the function reaches its highest or lowest point. So I want to remind you again what maximum and minimum values are for the function. So the greatest value the function attains is the maximum. So the largest value of y for the function. Okay, and the minimum is going to be your smallest value of y. Okay, so maximum and minimum. So it says over what values of x, notice over what values of x, so it's going to tell you, is the function increasing, for what values is it decreasing. Go ahead and make a t-chart and plot those points. So let's pick some values for x and y. We'll plug them in and we'll get y, and we'll take a look at this function. So again, I'm going to pick -6. First, I'm going to get my pen to go on. -6, -4, -2, 0, 2, 4, 6. You can pick whatever values you want to. And when I plug them in, I'm going to get 2. So think about it. If I do g of -6, just to remind you of function notation, that's going to be 2 subtract the absolute value of -6. 2 minus 6 is -4. So -6, -4. If I plug in -4, I'm going to get -2. If I plug in -2, I'm going to get 0. If I plug in 0, 2, 2, 0, 4, -2, 6, -4. And again, hopefully you will see the symmetric nature of this symmetry. Okay, so let's plot that. Zoom in to plot. All right, so there you see the V-shaped graph for the absolute value function. I'm going to go ahead and do my best to try to make this be as accurate as possible. So when you are graphing, and if you want it to be straight, after you graph it, if you hold it down, Notability should turn it into a straight line. All right, so it's clear on this graph that the absolute value, V, has a highest point. That highest point is called the maximum point of the function or the graph. And so I'll go ahead and indicate it for you right here. This is our maximum. It also happens to serve as the y-intercept. So some of our key features of functions can take on two different representations. So the maximum of this is at the point 0, 2. Now, we're going to get into more vocabulary later on. The maximum value of the function is just 2. The maximum location of the function is 0, 2. But the maximum value is just the number 2. So there's a little bit of a distinction between that, and we'll practice that. So notice if we go back to the questions, it says over what values of x is the function increasing? So again, I'm going to remind you that to the far left is negative infinity. To the far right is positive infinity on the x-axis. Notice it says over what values of x. So it's important to note here that we are referring, when we go to write the intervals, we are referring to the x values. So let's look at the x values just even in our table, okay? So if we look at the x values, right, over what x values is the function increasing? So it appears to me that the y values are going from -4 to -2 to 0 to 2. So here, I would say that the graph is increasing. The y values are increasing. So I'm going to go ahead and highlight where the y values are increasing. So I'll highlight that in orange. Okay, so the orange section of the graph indicates where g of x is increasing. The orange section of the graph is where g of x is increasing. Okay, I'll pick another blue. Do Bears colors, orange and blue, or my Illini colors. And here is where g of x is decreasing. Okay, so that's where g of x is decreasing. How do we describe those intervals? We're using x values. So the interval would be, so now again, think you read books from left to right. You interpret graphs from left to right. So the very left of this graph is negative infinity. So if you look at the orange part of the graph, we would say the interval where g of x is increasing begins at negative infinity and goes all the way to that purple dot, which is the maximum point. So negative infinity to 0. Now remember, these are x values. So look at this point here. The x value of that maximum point is 0. So the function is increasing. G of x is increasing from negative infinity to 0. And then the function turns. So it turns from increasing along the orange to decreasing along the blue. And so it is decreasing from 0 now all the way as it stretches out to infinity. So what's important about increasing and decreasing intervals is you're actually looking for where the y values are going up and down, but you're describing it using the x values. So that's really important that we remember we're using the x values. So when you write these intervals, these are x values. Okay, we're going to do a you try it to talk more about increasing and decreasing. So you can go ahead, each time I do this, you can pause the video and you can at least try to graph the functions on your own. That will be helpful to just practice graphing functions. And then you can rejoin me again when you want a second lesson on increasing and decreasing. Okay, so for the first function, I'm going to go ahead and make my t-chart. And when I make my t-chart, I'm going to choose some values for, that are simple values to use for f of x, so that we don't end up with points off the grid. All right, so that's kind of important. I mean, you can plug in anything you want to, but if you look at this, you're doing x squared minus 4x. So I'm going to keep my my t-chart kind of small for this one. So -1, 0, 1, 2, and 3. And then I'm going to see, and maybe I'll do 4. And then I'm going to see if that's enough to give me a picture of the graph. So when I plug in -1, so I would be doing f of -1. So I'm going to demonstrate again. Use parentheses. -1 squared minus 4 times -1. So that's going to give me 1 plus 4, which is 5. And then I'll go through and do that for f of 0, f of 1, f of 2, f of 3, f of 4. I'm going to do some mental math there. You can use your calculator, however you want to come up with those values. So if I plug in 0, obviously I'm going to get 0 because you can plug in 0. Plug in 1, I'm going to get -3. Plug in 2, I'm going to get -4. Plug in 3, I'm going to get -3. Plug in 4, I'm going to get 0. So again, I hope you see some symmetry going on with the y values. All right, so let's plot that. -1, 1, 2, 3, 4, 5, 0, 0. So hopefully you can see the U-shaped curve appearing. So you do your best. Hopefully you have the nice stylus like me. All right, so for what values of x is the function increasing? For what values of x is the function decreasing? So first of all, let's identify the fact that this parabola has a lowest point. This is the minimum. That's the lowest point on that curve. And it looks to me like it's occurring at the point -2, no, excuse me, +2. Let me get rid of that. +2, -4. And so if I were to shade now, so let me go back and use some different colors. So let's use yellow. So I'm going to highlight the section of the graph where f of x is decreasing. So f of x is decreasing along the yellow. And then I'm going to highlight this section of the graph green. And in that section of the graph, f of x is increasing. And at that minimum value, the graph turns from decreasing to increasing. And when we say f of x is decreasing, just look at the y values in your chart. 5, 0, -3, -4. See how they are going down? And then all of a sudden it turns and now they're going back up. From -4 to -3 is going up. From -3 to 0 is going up. So we would say the y values are increasing. So when you go to describe your increasing and decreasing, remind yourself, -infinity to the far left, +infinity to the far right. So the function is decreasing from -infinity up to that x value, Remember, we describe the intervals and we are describing the x values. Think about the fact that your eyes are tracking along the x-axis. So we're reading from left to right. Your eyes are tracking left to right. We are describing x values. So from negative infinity to 2, the function is decreasing, and then it turns, and from 2 to infinity, the function is increasing. All right, let's do one more, increasing, decreasing. So our second function that we're working with is our linear function. Again, there's another one of our parent functions that we're going to review. So let's go ahead and make a little t-chart, and then we can go ahead and graph that function. Again, we'll pick some simple x values to work with. And so I'm going to pick -3, -2, -1, 0, 1, 2, 3, and I'm going to go ahead and plug them in. Another option for you, if you remember, is to utilize y-intercept and slope. So the y-intercept here is 0, -3. So if you recall, that piece of the linear function is the y-intercept. So if I plug in 0 for x, I get -3. So 0, 1, 2, -3. Then I can go ahead and apply the slope, which is -2 over 1, which means I'm going to go up 2 over 1, up 2 over 1, up 2 over 1, and so on. And so if I were to plug in -3, I'm going to get 3, which is that point that I just plotted. And if I plug in -2, I'm going to get 1. And if I plug in -1, I'm going to get -1, and so on. If I plug in 1, I'm going to get, so think about that, you're going to go down 2 over 1. That's at the point -1, 1, 2, 3, 4, 5, and so on. All right, so I think we have enough points here to draw our line. I'm going to go ahead and connect it. Then I'm going to let Notability make it be nice and straight, and so on. Okay, so the question is, over what interval is the function increasing or decreasing? Well, let's go ahead and remind ourselves. Negative infinity, positive infinity. If you look at the y values, just the few that I put in the t-chart, 3 down to 1 to -1 to -3 to -5. And if you just visually look at the line is decreasing all the time. So as you go from negative infinity to positive infinity, we would say this function is decreasing. So lines have sort of a special type of answer for the intervals for increasing and decreasing. All righty. Last topic that we're going to go over is understanding the average rate of change over an interval. So your average rate of change is a ratio. Okay, so first let's write, it says, what is the average rate of change of the function over the interval? Use Pearson-Savas to explore this concept. Take notes below. So you can go into our Pearson-Savas, which is our online book, or you can just continue along with me here. So your average rate of change is a ratio. And it is the ratio f of b minus f of a over b minus a. All right, so let's talk about B and A and what that looks like on a graph. So let's go ahead and draw just the first quadrant of a coordinate plane. And I'm going to go ahead and I'm going to put on a curve, any curve. And we're going to refer to that curve as the function f of x. Could be called g of x, could be called k of x, h of x. We're going to call it f of x. And we're going to identify 2 points on that curve. So I'm going to identify that point here and this point here. This point here, I am going to label A, comma, f of A. Now, we don't know what the rule for the function is. So it could be, and we know that in this particular graph, it's non-linear. And when I say non-linear, I mean this is not graphing to be a line. This is not the graph of a line. So in order to figure out what that point was, we would take the x value and we would substitute it into the function rule, and we would get the y value, and we would plot the point. But since we don't have, we're talking about a general function rule, we would identify that point as a comma f of a. This point then we're going to identify as b comma f of b. In other words, a different input for that function. This interval, if we wanted to talk about the interval between A and B. So see how it says, what is the average rate of change over the interval AB? And notice there's square brackets around it. What that indicates is that the interval starts at a value of f of A. So it starts when x equals A, and it ends when x equals B. So this is what we're referring to. The total change of the function. I'm going to go ahead and make something that's going to look familiar to you. So the average rate of change over that interval is the slope of the line segment connecting those 2 points. And the slope of a line segment is determined by using the slope formula. This is actually the slope formula. Only it's using function notation, because this, and I'm going to highlight it green, the green is the difference between B and A. So A to B. So that's your delta X. I don't know if your algebra teachers ever called it that. And this, the yellow, is your delta Y. And we know that slope is delta Y over delta X. Change in Y over change in X. Rise over run. And that's what's going on over here on this ratio. It's a change in Y over a change in X. And that's what the average rate of change is. So it's going to be the change in the Y, so delta Y over delta X, which this is your Y values. Remember, f of B minus f of A, those are the values of the Y's over B minus A. And that is average rate of change. So it is the same as the slope of the line segment connecting A, f of A, and B, B, f of B. So average rate of change is just the slope of the line segment. So when you're asked to find the average rate of change, you are going to be given the equation for the function. It's going to ask you to find it over a certain interval. So this interval A, B, these are like your x's. So these are your inputs. You will input them into the function. Then you will do f of A and f of B. Those are your outputs. And then you will apply your change in y over change in x. So let's try one. All right, if we'll just pause on this question for a minute and come back so I can just demonstrate average rate of change. What do the average rates of change over the intervals indicate about the given functions? And then we can go back and address that question. All right, so let's go ahead and do the average rate of change over the interval -2 to 0. Okay, now here's the equation of the function, right? And so what we need from this is we need the ordered pair -2. So if I look on the graph, -2 corresponds to 1. And 0 corresponds to 1. So I'm looking on the graph. So if I do my average rate of change, so my average rate of change, it's going to be f of B minus f of A over B minus A. And so that's going to be y minus y over x minus x. So change in y over change in x. Now that's going to be 0 over 2, which is 0. And then if I go ahead and I do that for the next interval, which is 0, 3. So now I'm going to do it for the interval 0, 3. All right. So then I need my ordered pair. 0, 1, and then 3, 1. And then I'm going to go ahead and do my slope, my average rate of change. 1 minus 1 over 3 minus 0, which is 0. So look at my average rate of change it isn't different. That's because this is a horizontal line. And with a horizontal line, your average rate of change is going to be constant because the slope of that line is constantly 0. The slope of that line is constantly 0. Okay, let's try the next one. We don't need to do that last interval. So let's do the average rate of change for this line over the interval -2, 0. So that means we need our first ordered pair, which is -2, -2. I can pull it right off the graph, and 0, -1. And so now we're going to do our slope. So -1 minus a -2 over 0 minus a -2. And that's why in those prerequisite skills, I had you review slope. In the numerator, that's going to give me 1. And in the denominator, that's going to give me 2. All right, now I'm going to do my average rate of change over the interval 0, 3. And again, I hope you're starting to see the connection that 0, 3, those represent the x values. We go and grab the y values from the graph. So that's going to be 0, -1, and 3.5. And now we're going to do slope. So that's going to be 0.5 minus a -1 over 3 subtract 0. And when I simplify that, I'm going to get 1/2. So let's talk about that. The function g of x equals 1/2 x minus 1 has a constant rate of change again. 1/2 over every interval. That's going to indicate that this is a linear function. So let's go back up here. This indicates linear. Now you already knew it was linear because its graph is a line. But when your graph has a constant rate of change that equals the slope of the line, that's a way to verify that it's a linear function. In the previous one, this is a constant function. That f of x equals 1 has the same rate of change 0 over every interval. That means it's a constant function. All right, let's take a look at the third function here, which again, we've been working on these types of graphs, and we're going to go ahead and calculate the average rate of change. And we'll stick with those same intervals, -2, 0. Okay, so our ordered pair, we're going to have -2, 4, pulling that right off the graph, and 0, 0. All right, so let's go ahead and do our average rate of change. So that's going to be 0 minus 4 over 0 minus a -2. And that's going to give me a -2. So the average rate of change from -2 to 0. So from -2 to 0, that average rate of change is a -2. Should make sense to you. The function is decreasing there, so that average rate of change would have to be a negative. But let's pick the next interval, which is 0, 3. All right, so that's going to be the point 0, 0, and 3, 9. And let's go ahead and calculate that average rate of change. So that's going to be 9 subtract 0 over 3 subtract 0. 9 over 3 is 3. So now we see that we get a different average rate of change over that next interval. And that is because h of x equals x squared doesn't have a constant rate of change over every interval because it is a non-linear function. In fact, this is a quadratic function. Again, one of the family of functions that we will be learning soon. All right, one of those functions that is the parent function that is going to, that we're going to be learning soon. So average rate of change is the slope of the line segment connecting 2 points over the interval. So let me just show you that on this one. So the average rate of change, let's give it a different color, from 0, 0 to 3, 9 is the slope of that line segment. It's the slope of that line segment. And in there it was 3, but in the previous interval it was -2. Okay. You try it. What do the average rates of change of the function over the intervals indicate about the function? All right, so let's go ahead and find. And we don't need to graph it. We can find it just by plugging the values into the function. So here's our function. We'll start with the interval -2, 0. Okay, so that means we're going to have -2, comma, y, and 0, comma, y. And so what we're going to do is we're going to plug -2 into that equation and get our y value. So -2, absolute value +2, plus 2 is 4. And we're going to plug in 0. 0 plus 2 is 2. And so my average rate of change, I'm just going to go ahead and use m for slope, just to remind you that it is slope. 2 subtract 4 over 0 subtract -2. That's going to give me -2 over 2, which is a -1. So between -2 and 0, my average rate of change is negative. Now let's go from 0 to 3. So that's going to be 0, comma 2. So I'm going ahead and plugging in 0 for x. We already knew that. And 3, comma 5. Okay, let's do the average rate of change. That's going to be 5 subtract 2, 3 subtract 0, and that's going to be 3 over 3, which is a +1. So my average rate of change went from negative to positive. And then let's do the final interval from -2 to 3. So now we're looking at the whole, so we did the 2 pieces. Now we're looking at it from -2 all the way up to 3. So that would be -2, 4, and that would be 3, 5. And so that's going to be 5 minus 4 over 3 minus a negative 2, which is 1 over 5. So then that indicates that it's also positive. So if you think about this function, it's going to be a v function that's going to look like this. So from negative infinity to 0, its average rate of change is negative. From 0 to 3, it's positive. Overall, from negative 3 to 2, it's a positive 1/5. On the last part here, we have a summary of some of the key features. And so this is a good place to look back in your notes for what we've talked about in this topic 1.1. We've learned a few new functions. These are called parent functions. We're going to talk a lot more about them. Some graphs of them, domain and range, where they're increasing, decreasing, and where they have x and y intercepts. And then I want you to stop here and do not do the do you